Okay, we're very glad to have Professor Ness to tell us about representing data as measured using product formalism.
So, first of all, I'm speaking to a math department with people who prove theorems and, various, maybe are algebraic geometers or topologists or analysts. This may be rather far from what you worked on, but I hope I can at least give you an inkling of why I think data is so interesting now. And I got here by a long road through a master's in computer science. I worked in an industrial applied research lab, but I've been working on representations of data, hopefully using mathematical techniques now for some years. And this project originally started out as a grant that we had with the Air Force when I was at my previous industrial applied research lab. But I've kept going on it, and my original collaborators were Devasis Basu, Peter Jones, who's at Yale, and David Shellcross. And now I'm actually using some of these techniques on a DARPA project about information flow in social networks. So, but you can abstract it, so you too could do all this, all right? So I first want to tell you, there are 3 theorems here. But also give you examples of how this is applied to data. And just think moduli. That'll sort of give the point of view I'm coming from. So what is the motivating question? Well, in data, reproducibility of data analysis is really hard. Like you read some of these papers and you really, you wouldn't have access to the original data set. Furthermore, there's all this pre-processing that goes on to convert it into a form where you can really apply algorithms and and you may lose all the information you were trying to understand without actually meaning to do that. And so then if somebody else wanted to either understand the method or reproduce the results, it's very difficult. All right, so I certainly didn't solve this problem, but the point of view is, which I believe mathematicians will resonate with. Suppose you were, and data sets that's it. They're sets, because they're very complex sets, and sets are everywhere in the world. So they're really interesting things to think about, right? And representing them is a real challenge. So if you're going to pre-process your data, at least try to pre-process it into some representation that has a theoretical basis. So that there's a rich set of algorithms that can apply. Maybe it'll have several parts to the theory. So there's not only the representation, there's a visualization theory, or there's a noise theory, or something like that. And there's applied math. There are many ways to represent data, but I'm going to tell you about one. And sort of my other point of view is, not that I'm a statistician, but I know more than I did, is that the statisticians have been studying data for a long time, and they have a lot of ways to understand uncertainty, try to quantify it and things. So they're really valuable, they have lots of insight, right? But where I get stuck is I get these real world data sets and I don't know which statistical model to use. So in some sense, I'm just using a really general one that will apply to many cases.
If you want to see,
yeah?
just touch the peg or something.
Okay.
Okay. All right. So, so let me just, not that you need this slide, but let me just remind you what a measure is. So if you have a non-negative measure on any set, it just, and you have a sigma algebra, collection of subsets that are closed under intersection, countable using intersection, right? It assigns a number, a size to each of those sets. That's all it does. But with this mild constraint that if you have 2 disjoint sets, it's additive, right? Now, suppose you have a finite data set. Can be very, data sets in the real world are finite. They happen to be huge, and they may have lots of structure that you don't quite know what to do with. But so how would you take this data set and represent it as a measure? Well, there are some, elementary ways. Your data set, you say, well, it's part of some universe. And so what could I do for all these subsets I'm interested? The size could be just the count of the number of points. That's a really elementary way, but it's like counting measure. So that would be a way to represent a data set as a measure. Another thing is lots of times you have a function on your data set like time series, which will have a bunch of points coming in over time, but you have measurements at each of those points. So you can add up the measures of all those points over a set. You get another measure. And then sometimes, like for time series, this happens all the time. So time series is on a unit interval. You partition your interval, your set up into some fine set of pieces and say, well, that's the finest scale I'm going to go to. And you can compute the averages over each of those and then construct a measure from that, because that's just a step function. So the only kinds of functions I'm using are really simple functions. So these are examples of ways to take a data set and, in principle, represent them as a measure. But now you say, well, you know, if you look at a measure theory book, it's like very abstract. There are hardly any examples, although Patrick Billingsley wrote this beautiful measure theory and probability book. He's a mathematician, beautiful. So, and he does lots of examples, and many of his examples are really about the rational numbers. But that's basically all I'm using. So in statistics, you think, well, I have a family of distributions, like a family of Gaussians, and they're characterized by their mean and their variance, right? Well, so it would be nice if these measures are in this parameterized family, so it's not just this one-off. That's where this sort of idea of moduli comes in. So parameterized families are great, because if you have a huge parameterized family and you have a lot of different samples of data, you just, in principle, take each data set, represent it in terms of those parameter or moduli, and then you can compare your different data sets, you can work on that, and it, you know, and the parameters are hopefully nicely normalized and things, so you can compute with them, they make some sense to you. Then another big problem you hear about is, well, how can I fuse my data sets? Well, if you have different data sets and you've represented these parameters are in big space, moduli, and you just put them all in there and study. It's like studying the space of all curves or something like that. So anyway, and another thing is machine learning classification problems are huge. So you can actually, but to get started using at least well, even I think for neural networks, but to, you know, the support vector machines where they basically draw a line in high-dimensional space to separate their classes, you can use these parameters that you computed via some rational method that makes sense to you as features. And they're automatically computed. Now, domain features are really very useful too, but it takes a long time to think of them. And so there are many things you can do once you get it in a nice big parameterized family. So there doesn't seem to be any universal parameterized family of measures, but there's one that's a really big family, and this is the one I'll use. So it's measures on dyadic sets. So what's a dyadic set? Well, on the left I've shown a picture. You have a set, and now you have a collection of subsets. It basically has a tree structure. So here's your whole set. You've broken it into two disjoint pieces. They all look like they're the same size, but they don't have to be. Each of those into two disjoint pieces. They form a binary tree. This is good because if they form a binary tree, you can probably program it up really fast, because if there's one thing computer scientists have studied, it's algorithms and binary trees. And now we assign a measure to each of those sets, but the measure of the left and the right child, the sum of those two is the measure of the parent. And you look at this, and really, if you just choose a scale, a level in your tree, you know that the sum of the measures of each of these add up to, say, 1 if it's a probability measure. And so it's like a histogram. So basically, you're using these histograms at various levels. The multi-scale part comes in that you say, well, I don't really know which scale I should look at my data at, because, you know, if I look at sort of this time scale, I might see something, or that time scale, I might see something. So in this approach, you sort of represent it at all scales, and then you figure out later which scales were revealed which things. Okay, so now we're looking for a nice set of parameters. Okay, so there's a really simple way to get a parameter here. So you can take, a node, and you take the measure of the left child minus the measure of the right divided by the measure of the parent. So this is just the difference of two conditional probabilities, the probability that you're in the left minus the probability that you're in the right. And you don't need to save the sum because you know that adds up to 1. So this, you've just extracted the information. And this tells you sort of the imbalance or the skewness. Okay? So now what happens if, sometimes you're going down the tree, there's no measure there. So if it's 0, we'll just say the measure of parameter of such a node is 0, and then everything below it's 0. Okay? So those are measures on dyadic sets. And okay, now here's a really simple example that sort of justifies this parameter a bit more. So here's a histogram. It just has 2 parts, measures a fourth, 3/4 adds up to 1. And you sort of say, well, the measure of the left is, the naive thing would be half of the measure of the whole thing. So I put the half in, but then there's a correction factor because it's probably not a half. So we'll write it as 1 plus a. Then the measure of the right is 1 minus a, and you solve and you get this parameter. That's another way to think about it. And this is just saying that the simplest measure you can think of is the one that just splits everything equally. But now this formula looks even nicer if you use this little Haar function like this, which is 1 and minus 1, which you can, anytime you have a set broken into 2 pieces, you can define one of these. And then you can put these 2 pieces of the formula together and you get one nice formula. So that's the product formula. So now I have parameters. Okay, so now if I want to use this, what do I have to do? You have a data set, and you have to repeatedly divide it into 2 parts, mark them left or right. But usually there's a way to do that because, people think binary features and things all the time. So this is very natural to do in many, many cases. Okay, so then there is this theorem. Actually, this is a lemma, okay? I should have said lemma. This appeared in an annals paper at the very back of a long annals paper by Robert Pfefferman, Carlos Koenig, and Jill Pfeiffer in 1991. So they were really, working on Dirichlet problems for elliptic equations. But they were trying to prove a theorem, and they needed to produce an example, basically a counterexample to what they're doing. And so they proved this lemma. I'll just go through it more carefully. They proved this lemma, and they used this as a way to compute explicit examples of measures that provided the counterexample they needed. That's how they did it. So the theorem or the lemma says, if you have any non-negative measure on a set with this, dyadic tree, an ordered binary set system, then it has a unique representation as the measure of the whole set, which might not be 1, it might be something other than 1, times this kind of product formula. And these are these parameters, the conditional probability of being on the left minus the right. And furthermore, any assignment of and the parameters are all between -1 and 1. So they're nicely normalized. If you have any assignment of product coefficients in the open interval -1 and 1 to 1, you get a positive measure, so there are no pieces with 0 measure. And so that means you can randomly sample from this space of measures. And you can, test out your algorithms, random samples. Now, if you are at these endpoints, that means that some of the sets have measure 0. So if you want to say that any assignment of product coefficients would satisfy the case that if you basically create a set of measure 0 over here, the tree under it's all 0, gives you measures. So this means you actually have to randomly choose a tree structure for the subtree that gives the support of the measure. Okay? So That's your universal theorem. And notice, like lots of times in statistics, you add. You have mixtures of distribution, mixtures of measures, Gaussian mixtures, and that's an additive theory, and this is multiplicative. So this came out of, there's another sort of avenue into this. It came out of work by Levy, I think, and Kahan.
So I remember what the A's are, but what are the H's?
Oh, those are those little Haar functions.
Okay.
And this is, you put those in just so the formula becomes much more compact. Okay, so here's an example of a binary tree with the parameters indicated. So how do you, if you are given the parameters, how do you recover the measure, the sizes of the sets? Well, at the top, this is your binary tree. At the top, at the root node, you store the measure of the total set. And then you just put labels on the edges going down where this is the parameter at this node, this is the parameter at this node. And the formula is it's 1/2 times 1 plus the parameter at this node here, 1 minus, you're going left and right. So you just multiply these factors going down and you recover the measure. Okay? Now, what's the real mathematical content of this is that even if the binary tree is infinite, the measure converges. And it converges in this weak star sense. So, and compared to what was done in the original Annals paper, what's slightly different about what we did was after I used this for a while on time series, where they just did it for the unit interval. And they didn't really discuss the importance of the parameters. They just used it to get their result. But two things, after I used this for a long time, I realized, this really just works on a binary tree. It's completely general. And also, we want to use it where the measures aren't all positive everywhere, because that's the way the real world is. But you get convergence to a measure even if the tree is infinite. So that's the mathematical content of that. So these parameters have all sorts of, you can randomly sample, as I mentioned. Actually I learned last summer, although I haven't actually coded this up yet. So there's a mathematician named Sant'Ambrogio, who is from Orsay. I went to another conference and I was talking to him about this. And there's this very general distance, like if you have distributions, you say, well, I would want to measure a distance between distributions as well. So there's this Wasserstein metric, which is, we read a general definition, really general, impossible to compute, right, but works on a manifolds, and Villani, for example, did all sorts of things with it theoretically. But Sant'Ambrogio says there's this very tractable formula. You can explicitly compute that in this case, which I haven't actually programmed it up yet. And then you might say, well, let me try to see imagine how this might work. So what's a very simple yet weird kind of measure? It's a Dirac delta measure where all the mass is at one point. So that requires, and that's not a traditional Born-Randall measure, but that requires an infinite representation to get there.
But this distance coincides with the norm of the difference of the two measures?
Oh, okay, so the real distance to use is the Wasserstein distance, which I didn't write down the formula, that I haven't practiced with it enough to write the formula. But anyway, if you're interested, I can discuss that with you later. But if you want to give an approximation to the distance, there is another distance function which sort of approximates the grandiose one that you should really use. And you have all these, now you've just converted your data set. You've got a data set in a binary tree structure. You represented it as these parameters. So, it's just you represent it as a vector in a high dimensional space. That's all you did, because you just write down all the product coefficients in order as you go down the tree. So now you're in a vector space. All the representations, the values are between -1 and 1. You're ready to do math, okay? But so you just use the natural distance, the Euclidean distance. That gives you
If I think of them as measures on the Cantor set, isn't that the same as taking their difference?
Is measures
norm
in,
of the
I think the answer is yes, but I'm not completely sure. But okay, you are right. Something I don't understand as well as I should is this is related to fractal measures. Yeah, you know, there's work in that direction now. You know, in real life, your fractals require an infinite dimensional tree, and I'm always working on finite trees, so I don't think about that too much, but you can, right? Okay, so here's a real data set now. So this is a time series. So what this graph is showing is wind data from a particular location in New Jersey at a particular altitude, and it's for a year, and the wind speed was recorded. So this is the graph. It doesn't look like very smooth or anything, so it's hard to do calculus on this, but that's the way it looks. That's the way time series usually looks. So now this whole setup applies immediately to time series, because when you do time series, you usually choose a window. Like in this case, I'll show you. I think we chose a year, right? So it's a unit interval, in other words, and you break it in halves, quarters, eighths, etc. Right? In fact, in Billingsley's book, that's the example he does over and over again. And when you break your window up in halves, quarters, eighths, etc., it's the same thing as asking where the binary representation of the number has a 0 in the first position, or the second, or the second position or not. So you're just doing, you can pretend you're just working on binary rational numbers if you want. So, okay, we wanted to compute this representation. So this is, I think we took the data for the whole year. Yeah, we took the data for the whole year, and we chose 4 different days of wind. Actually, the colleague that worked on this example with me cleverly chose these 4 days, so that the wind speeds look rather similar and the wind speeds look rather similar. Now, why is this less wiggly than the one you saw before? And it's because we just represented them down to some scale and averaged at these fine scales, so they look a little less wiggly. So these look sort of the same, but they're still very wiggly. No good calculus function to that you study in calculus to represent them. And so we just computed these parameters. In other words, what do? We divided this into halves, quarters, and in each of these fine intervals, I went down to 2 to the 6th or something, computed the average wind speed down here. When you have a step function at that level, that's a measure. And so you can just apply the whole thing. That's all we did. So these, and then you can color code these, because these parameters are between -1 and 1. You know, you can say green is 0, red is 1, blue is -1. Anyway, the point is, now why use these day wheels? Because at the top of the tree you have 1, at the next stage you have 2, next 4, so the day wheel works. And just color code the parameters, and you look, and you say, oh, these 2 look pretty similar, and they are. And these 2 look rather similar, and they are. So it's just so important to have visualization techniques, because it's really hard to understand this stuff, and you're just trying to sanity check what you're doing to see if it makes any sense. But furthermore, there's a whole subject in statistics called like trend analysis. But this is a very crude kind of trend analysis, because what's the trend here? It says in the bottom 2, there's more wind in the first half of the day than in the second. So the area under this part of the curve is bigger than the area under this part of the curve. So you do left minus right over the total, you know this will come out to be positive. And that's blue in the center for both of them. But up here it's green, because it's about the same. But furthermore, even when you're just in the quarters, there's still more wind in the first quarter of the day than the second. So this part is blue. But over here, there's less wind in the third quarter of the day than the fourth. So this part is sort of heading toward red. So you've just you know, and you didn't know ahead of time. I mean, maybe you could look at it and say, I would see these trends, but if you're just computing away, it picks them up for you. So it shows you wind patterns. This is another example. So lots of times when you have time series, you don't just have one, you have a whole bunch of them. And this problem was we got data off our IP network at work and from a particular port, and the systems people sort of had divided the IP addresses into 6 groups, no, into, yeah, 6 kinds of groups. And so we wanted to see if we could sort of, if we could have figured out which IP address it came from, or at least distinguished it based on, you know, based on these parameters. So we had, we got 12, we have 12 rows here. 12 rows means there were actually 12 time series. And we just, this is a window, and we just did it down to some scales. So scales 0, 1, so 0, 1, 2. So that meant the bottom row had 4 nodes in the tree. And then all I did was we had these windows of these measurements, of these 12 types of measurements for, I think, a couple weeks, I guess. And I just took the measurements for each IP address and just averaged them. Just averaged the representations, because I wanted to see, does it even make sense to try to do this classification problem? So I just averaged them, and lo and behold, the averages look different, although some definitely look more different than others. So you can see that, well, this will be subtle, but should be possible. It'll be really easy to distinguish this one, etc. But that's another point about this representation. So we've gotten this represented the data as measures in terms of the parameters. And then if you average numbers between -1 and 1, they're still between -1 and 1. So you can compute average measures easily. And this is just an example that it can be really useful. Okay, last summer I did this example. So what's the data set? So here's what you see over here is a room configuration scenario. So this was, I got this simulation data from Professor Mubashir Kapadia at Rutgers in computer science. And he wants to simulate crowd behavior, especially the behavior of a crowd exiting a room, which is certainly important these days. And so in this room, you might see here, there is an exit here. And a student had written this program where he could, the room was this shape and had these subrooms, but then there were these obstacles and things where he could reconfigure them. So he generated, he ran his simulator, and using 20 different configurations of, or I guess 19 different configurations of the obstacles. So I just wanted to, you know, the question was, would there be a way to attribute the difference in the crowd flow behavior to the obstacles? That's of course, and you want to predict the exit time. All right, what this analysis doesn't really solve either of those, but it hints at groups you might look at. Although I will say, some people following the workshop last summer used neural nets, and they actually accurately predicted the exit time for the room. So the way I thought it was, you have a bunch of flows of people through this room. This is all time series. The method still applies because you can break it up into halves, quarters like this, over and over, so still dyadic tree. And so I got all these time series of people exiting the room, their x and y coordinates. But I said, well, they're really trying to converge just to the delta distribution that's actually at the exit. So I just measured the distance, computed the distance of each of those to this exit distribution. And then I averaged it for each of these 19 scenarios. And then I regenerated the time series from that. So the point is that when you look over here, there are sort of 4 different, this little group here, a group here, a group here, and a group here. Now, it would have been wonderful if we could have attributed, said the features for these rooms are really different. We didn't really get that far because I didn't have a really good way to quantitatively characterize all those features, but that's what you'd like. But the point is you can do lots of things with this if you think about it. And this is all unsupervised. I just computed away and these patterns emerged. Okay, and then the last type of example is the following. Just to indicate that you can apply this to a huge set of collection of data sets. Many data sets, your data is represented as binary features, like you have a whole bunch of people and they have some attributes and either have this or this or this or this or this or this. So you represent the data in terms of vectors of ones and zeros. But if you do that, and if you happen to order your features, so then you can say, well, there's either the subset of the data that has, for which the first feature has value 0 or 1. Then the second feature, you look at the subset of those for which the second feature has value 0 or 1. So you get a big tree, so you can use this method. And I used it now, but then somebody might say, as they do often, well, what if the features are in the wrong order? Because I thought about it and I really want to rearrange them. Well, that's exactly what they do in Bayes' formula. In Bayes' formula, they usually have 2 orders, but this, you have many more to rearrange. So there's a way you can actually compute this and things like that, but that will come up. And then some of you must be topologists. If you represent your data this way in terms of these feature sets, actually these feature sets are disjoint, binary 1, but what often happens is you have these natural subsets or these features, but well, the individual features are 0, 1, but you're really interested in where the support of these features overlap, the intersections. So if you look at the nerve simplicial complex, you look back to this tree, you forget the measure. You just remember whether the measure is 0 or 1. That's all you remember. And that gives you the nerve simplicial complex. So you can use both this kind of representation of measures, and you could go off and compute computational topology statistics on it, which I did in one example, which you get much more abstract set of statistics that's independent of the order of the features, by the way. So I haven't really done more on this. I also think that somehow this is related to privacy, but I haven't quite figured that out. So I did this they don't look super different, but I did this for a data quality set. So the problem was these people had given a Rutgers team a set of data from a database that was absolutely crucial to their operations in this government agency, but they had really not designed the database with a set of correctness criteria constraints. So they reverse engineered that, and then those gave the correctness criteria constraints gave me the feature sets, so I used that to represent the data. All right, now there are just 2 more theorems that I want to mention rather quickly. So that was all about the basic representation theorem, that it's, I think it's very easy to conceptualize. The set of parameters is really, these parameters are not computed, they're computed explicitly. They're not computed by optimization. Well, optimization is extremely powerful. It's used like neural nets all over the place. However, you tend not to understand what you get after that. And this, you understand what you get. So, and I also think there's a way, I just haven't sat down and worked this out, to take these trees that they use to describe the neural nets to actually reformulate them this way so that you can say, well, I could actually, there is a tree, there is a measure there. Because people that, they use, like Sanjeev Arora, who's an eminent theoretical computer scientist, who's really proving things. He's really proving theorems about deep learning, which is very hard to do. But one of the obstacles to making progress in certain areas is that they don't understand the distribution from which the data was drawn, text data, image data, etc. If they had good characterizations of those distributions, they could prove much more, right? And then they always say, well, if I wiggle my neural net a little bit or something, it's not so stable, right? What will happen? So, you know, when you represent your measures this way, you can look at the parameters, and the measures might actually be very close together. They may be actually hard to distinguish. In other cases, they say, well, we don't seem to need many samples, right? We only need not nearly as many samples as we think we might to distinguish the measures. It's probably because the underlying measures are really very far away. So, but this is often a different direction. So, point is that visualization is very important for data, and because you just need this crutch, and people think about data, and it's a really cognitive science. So this is a theoretical result in that area. So the bottom line is that now if you have these nice measures on unit circles with this dyadic structure, there's a way to represent them almost uniquely as Jordan curves. Okay? That's the content of this theorem. And this really is, this is really due to Peter Jones. To prove this theorem, you know, he says, well, the proof is really in a book by Alfors. It's not so easy to dig out. But the idea is if you have the unit circle, which is just like the unit interval closed up at the ends, right? And suppose you have a measure on the unit circle. So think of that measure. But then think of that measure as basically representing a derivative of a function. Suppose your measure, or your differential, is the differential of this nice function phi. And now if you assume that this measure is sort of nice, it's like positive everywhere, it just doesn't have a direct mass somewhere, etc. So then that says that this function is really a homeomorphism of the unit circle. So then the way he gets to a Jordan curve is he says, well, he started out with this circle. He has a Riemann map from the unit disk to the inside of the curve, the Riemann map, the map from the unit disk to the outside of the curve, and then he inverts this. It takes the original first one, going from the unit circle into the unit disk, and then goes back by this one. And he what do I do now? Right. Okay. So that's the way you get the curve, is because you have the measure there and you do this mapping, so you get the curve. And you have to solve the Laplace-Beltrami equation along the way here.
Okay, so what's in Alfors' book?
So
What's the solution to?
yeah, the proof that what's in Alfors' book is the proof that you get this mapping to the curve this way, the construction of the curve this way. That you get it's called the Welding curve. So you get these Welding curves by this method, and that's the proof that's buried in the book of Alfors.
So this is unique in some sense?
Almost unique, unique up to Mobius transformations.
Absolutely.
Right. So, right. So now you could, okay, there are, like Mumford and some of the work he did on vision, he was constructing curves. So you can just blast through, and some people know how to actually solve this. And so you can construct this mapping explicitly. But in case you don't understand, you don't have access to those tools or understand that method, there's a simple way that you can approximate this curve representing your measure. So it's a snowflake curve. Your measure, you can think of it as being on the unit circle or on the unit interval. And so you say, you draw a little triangle and you say, I'll raise it by the size of the product coefficient at the root. Then if it's plus or go negative, you go down there. Up here, you raise that or lower that by the size of the product coefficient. So you get a kind of fractal curve. And that's an approximation to this Welding curve. Now, we did that for this LiDAR data set, and you know, it doesn't look like super informative, but it can be done, and I just haven't used this method a lot, so I can't really give you a lot of intuition about it.
Measure as a measure on this circle.
What?
You're thinking of your measure now as a measure on this.
On the circle, right.
Corresponding to this diagram that you
Right.
showed us?
Right, right. So there is, but the point is, unlike, there is a visualization theory, at least this type of visualization theory, that goes with the representation theory. And usually a theory for visualization is completely missing. So that's really the point here.
So, where are the Jordan curves in this?
Oh, the Jordan curves, so you would have to close them up. I mean,
okay.
This is an approximation, so I just did it. I would close them up, and that would be,
Thinking of that is maybe, a cylinder.
yeah. All right, so, yeah. All right. So then the third theorem is this multi-scale noise model theorem. So another thing with data is lots of times people say, well, I have this data, but, you know, the principle is you were like measuring it. I mean, okay, lots of times statistics, they say, I do repeated measurements. Well, in practice, people just give you a data set. You don't have repeated measurements, you have that. That's what you have. But suppose you had repeated measurements, then there's probably some mistakes, right? So then there's a little noise. So then they add a little Gaussian. But you have no, even if you happen to know the measure that you were starting with, you add this little Gaussian, you have no idea which measure you're still in. So this is there's a way to, there's a noise model here where the noise model is simple. You have this, all these product coefficients at the nodes of the tree, and you just multiply each of them by these factors where this z is a Gaussian. So you have one Gaussian variable for every one of the nodes on the tree. That's a lot of Gaussian variables. So you're going to have lots of room, you know, many, many dimensions along which to wiggle. And this is the variance of the Gaussian. And this is this Haar function for the set. And then you subtract off this quantity because that makes this, that makes this theorem work. So now if you had your measure and you multiplied it by those factors at each node, because at each node not only do you have the parameter, you also know the size of the set. So you're actually measuring, you're actually multiplying, you know, changing the size of the set by this noisy amount. You're wiggling it, okay? Well, it's still another measure. And so the point is this noise model gives you another measure in the same family because the family is so big. But now there is this theorem that can be proved, and the assumption that you need a special assumption on these variances here. So when you're going down the tree, you choose the Gaussians by which you wiggle to get the noise independently, but the variances depend only on the level in the tree. So we have one at the first root. So they're scale dependent. Okay, suppose you have scale dependent noise, and then you might say, well, I have this noisy measure. Okay, I have it figured out. I could, in finite paces, I could just blast through and use the computation before and figure out exactly what the, you know, if I sample from the Gaussians, I get a measure, I can compute the representation for each one. But what you're really interested in is how much does that actually measure vary from the original measure? And the answer is, in expectation, the noisy measure agrees with the original measure on all of the sets. And you always have to do this at each finite scale. So you can compute and this computation of the expected value of the measure at a set somewhere in the tree is easy for two reasons. Okay, because it's scale dependent, when you go down any path in the tree, this one or that one, these sigmas, the variances are the same for both paths. So that makes the computation easier. The second thing is that these variables, these Gaussians, are independent. So you can multiply. And the third thing, actually, that makes it easy is because you're raising all of this to an exponential. So when you go down a path in the tree, you're multiplying exponentials. That means you're adding what's in the exponent And these are log normal distributions. So there are formulas that tell you how to compute the expected value in the variance. So, and you might say, well, you know, I'm wiggling left or right here. But in fact, this formula for the mean for the log normals depends on the square of the variance. So you're saved. So this, just I wait, oh yeah. Okay, all right. Okay, so an expectation, this agrees. And then there is a bound on the variance also for the, I just did the bound on the variance for the whole set, but you could sit down and do it for every set. So there's a bound on the variance, and the point about this formula is it just depends on the noise parameters, this 4, and this R, which is the support ratio. So in your measure, you know, a proportion of the nodes might actually have 0 measure, so you just compute that proportion. So you get a bound on the variance. But then, you know, the content is, well, what happens when I take the limit? In other words, is let the tree become infinite. And what you can say is, in expectation, all the expectations are just come from an actual measure. So that allows you to take this Wheat star limit and conclude that it has non-zero value. Now, the simplest case of this is where you just start with the usual Lebesgue measure, you know, in other words, halves on each left and right, quarters, etc., right? And then you just add all these noise you just multiply by all these noise variables. And Kahan in like 1985, I think he was a student of Levy or something. So he worked out this sort of multiplicative theory of chaos, and they were trying to make sense of what Mandelbrot had done. So they did that. So he developed this theory of chaos, and this is but he didn't have access to this explicit representation of measures at the time. So he developed this theory for chaos. It's a rather similar distribution, but the hypotheses of the things have to be different. And but this model of chaos is actually used in various statistical physics and things like this to get measures. So now I think one practical thing, like I haven't done this yet either, but so if I can figure out a way to just explain how this connects with neural nets, I hope I can do that, because that will enable me to really feel like I understand them to some degree. One of the problems there is they're so huge that you need training data to do this classification problem. That means that you need a huge amount of training data, more than you have. So, but if these noise models just mean that, you know, you can generate lots and lots of samples of measures that are if you get a characterization of the way you're actually constructing a tree on the data, that's the same thing as having a measure, right? And then you get the parameters, and then you can do this noise model. So you could generate many, many samples. So that might be useful. So that's really so the bottom line is that so I guess where's my summary slide? Okay, so I'm trying to point out that I think you can use mathematical structures. I think there are a lot of results that are still not surfaced in mathematics, because mathematicians are extremely good at representations things. So you can think about that and exploit that to come up with representation techniques for data. And I think it's much richer than is what's currently been surfaced. That's the bottom line here. And this is an example of that. It would be nice to make, and while you're doing your theory, you might as well include in the theory something having to do with visualization and noise too, because they're very, very important aspects of data analysis. So we had a representation theorem just in terms of binary trees. You know, the formula for the parameter is truly simple. It's recursive. You can just sit down and program this up. It's like really easy. And so students, I've taught this to undergraduates. I just explain them and explain the formula to them. They go off and write their little recursive program. And so then they, have something where they can actually do data analysis on very general types of sets. And it's just really easy to use. So that's the first part. Then I got this is the visualization by the Jordan curve, and then the noise model. And it really applies to lots and lots of kinds of data sets. Now, there's always a chance that when you represent in this family, the data really was like a sample from some incredibly well-known distribution. Unlikely, but possible, right? Gaussian. So you could take any, this is another thing you could have undergraduates do. I've never had them do this, but you could sample from the well-known distributions, right? And compute this representation and see how those distributions compared. So I think there are a lot of projects buried in this. Okay. Now, I want to thank you, but this is just something, slightly different. Okay, this is, I'm sure most of you are teaching linear algebra or have taught linear algebra. So it's so important. And when you teach linear algebra, I would just urge you to spend a day or two teaching them principal component analysis. And if you don't really know what that is, which is, it's just like SVD, you compute singular value decomposition. It's really what it is, it's slightly normalized slightly differently. A very fundamental technique in statistics, and it's explained really well in this new version of this book that Peter Olver just finished writing on applied linear algebra, partly because I said, is it in your book? And so he really put more into that chapter. It's now, but so we did this experiment last summer, this team at the Wisdom Workshop last summer. And so here's a picture. All right. So the moral of the story here is if you do singular value decomposition, instead of computing the eigenvalues, if you have a matrix that's not square, you can do singular value decomposition. If the matrix is symmetric, you get the same answer, but otherwise slightly different. You put it in this normal form. You have these singular values then on a log of eigenvalues on the diagonal, right, arranged nicely in decreasing order. Those are the information. And what you can do with data sets is since the SVD theorem is, in all the, like MATLAB and everything, right? If you have a data set, you just write a matrix where each point is, each row is the coordinates of the data point. So of course you can compute SVD if it's not super big, not too big, but then you don't need to stop there. You can do it over and over again on smaller and smaller subsets. So here's a picture where we wanted to use it to relate this to dimension. Because there are a lot of people in math who think, the group of people who are using manifold learning to represent data. But the papers that have theory, a lot of them assume that the data lies on or near a manifold, which is like, how do you know that anyway? Maybe it lies on or near a bunch of manifolds, and then it would be near some nice variety or something. But we sampled from the sphere. We had these, this line segment sticking out of it. And so what we did was computed SVD over and over again, meaning that for each point, took a bunch of balls, a radius going down repeatedly by ratio of half each time. And for the data points in that ball, computed SVD and looked at, and computed the number of singular values which account for 95% of the total norm of the singular values. This is the same thing as saying you're accounting for 95% of the variance in PCA. Okay, and then we saw what the minimum was as you went over these balls. And now we color-coded the result. And this is a way to pick up, this is purely heuristic, right? But the point is it picked up dimension very nicely. And there is a whole bunch of papers on intrinsic dimension, many of which some of which I can understand. Others, I just didn't code them up and things. But this is such a simple way to do intrinsic dimension. It would be nice to have some theory there. But I think, you can do examples of the curvature of the sphere and things like that and justify it this way. Okay, but then we took this LiDAR data set. So this is bouncing light off things. It's like radar, but coming back. And this is the image of the Golden Gate Bridge. Took this data set and just did the same thing to compute the intrinsic dimensions. And sure enough, these came out to be 1, this like sort of 3 at these nodes. These for some reason are 2. So the possible relevance of this to manifold learning is you say, well, it's possible that my data lies on or near one manifold. That seems a little simple, but that is it actually happens in some cases that that's true. It seems slightly more plausible that it lies on or near a bunch of manifolds of possibly different dimensions. And some of them might be very small, very big, and they're all connected together in these weird ways. But if you want to do this analysis, the first thing you have to do is to go into the data set and pick out these pieces. It's like clustering, but you want to cluster for dimension. So this is a heuristic, but at least principled way to actually do that. And by the way, you can teach principal component analysis in linear algebra, and the students will come out knowing a really important statistic. And this is usually not done from my informal polls. And I think that on the other side, I don't really know how they teach in statistics, but I don't think they're related to SVDs. I mean, some of the statisticians really know this, but a lot of them don't. So it's just my little plug at the end. So, all right, thank you very much.
So any questions or comments for anyone?
Well,
So when you look at the parameters that you get, say going back to that wind data, what can you read off from the data about the data set from these
parameters?
So for example, I mean, if it were linear, then presumably it would all be one color or something like that.
Well, actually, I'm not sure. Okay, so what you can read off from those, the parameters, like each separate parameter just tells you like the difference in the relative volume between the left and right. So if it's big, it says there's a big change between the left and right. So it sort of tells you the scales and localities at which something's happening in your data. You know, in other cases, it might be sort of flat because the parameters are all 0. It means that the volume of the left and the right are just equal, and not a lot of remarkable things are going on. So it can point you to where anomalies are occurring and things like that.
Like, for example, suppose it just exactly fit a polynomial
Yes.
degree n.
Yes, I haven't
Would you
actually.
be able to just tell that this is a polynomial degree n by looking at it?
I actually never sat down and worked out this example, but let's do linear first. And I haven't really sat down and calculated this example either. I think there's a formula where you can induce linear, but I have a feeling that it works better if it's on an exponential curve, because this theory is basically multiplicative. So the first case I would try is to do it on the exponential. But another point is that the data is like multi-scale. It's sort of this fractal idea that it looks different at different scales, and that's the way the data looks. But yeah, I think the other thing is, like in the trend analysis, the statisticians do they have a time series, and they want to say, well, there's a change point here, so it looks sort of like it's on a line here, and then it tips like that, and that's the change point, and this is a trend, and this is a trend. But so this measures trend by sort of doing this volume computation, like the volume of the left is bigger than the volume of the right, so it's a little more general. But anyway, I like this because this has helped me learn much more statistics than I would have learned otherwise, because I have a representation I feel like I understand. It's simple. I could teach it, explain it. I could apply it myself. I can write my own code. So then I think, well, why are they talking about that or that or that? So it gives you a way in, both to statistics and to some of these machine learning and these AI techniques. So, and it's easy to teach to undergraduates. I mean, it really, you could assign these exercises, they can do these experiments, and it empowers them. They can actually do something with data sets. Right now I'm trying to use it on this social networking data. So you might say, what's a social network? Well, okay, so the interesting thing about that, I finally figured out what's interesting about these social networks. So we're given GitHub data, meaning people put their code online. So the first thing that's interesting is like in Twitter and in GitHub, other things. So the computing platform actually provides, data structures for the people, very general. You can put like a little text message up there, you can do some little links and things like that. They provide you with the data structures. The people are the programs, so it's a random programming model. So who knows what's going on? That is actually the problem. Okay, and could all these companies do they actually know what's going on? Probably not. So we're supposed to construct this model of information flow based on this GitHub network and predictive. So I looked at it, and at least it's all time series. I mean, there are like a zillion time series, and who knows what they are, but we're trying to, and now we have to predict. So, we're saying, well, if we know the parameters on the left, 3/4 or something, the interval, could we predict the parameters on the right? We don't know if this is going to be a success yet, but at least that's sort of how we're bringing it to bear. And the computer scientists actually like this because it's based on binary trees. So they, are very comfortable with and know a lot of algorithms for handling that. So again, it's like it's possible to at least think about some of these things more than you imagined otherwise.
What does the Jordan curve give you?
It just gives you I haven't really used it a lot yet. So it gives you a way to visualize the measure, really. That's the point. And I haven't...
Is it computable?
Well, that's a good question. So somewhere, some paper, yeah, there's for example, what's this called? Okay, yes, it's computable. And I forgot there's a reference, for example, Mumford sort of did it, but he has references to software. I wrote it in some paper. I can send you the references you want to know. But another point is by doing this little fractal technique with the snowflake curve, you can approximate it. And this, like mere humans can do, is like little splines. So that's easy to do. Like actually sitting down and proving that that's really a linear approximation. I personally can't do that computation, but in principle, apparently you can. So thank you very much.